Okay, so welcome to my tutorial, and today I'm gonna talk about calculation of double integrals such as this one in C++. This is kind of demanding on how to do that. Regarding the code, it's quite easy, but you have to know the algorithm. Well, let me start with simple integral such as this one. So let me draw a picture how numerical calculation of an integral looks like. It's actually a sum. Assume that we have some function such as this one, and we are given bounds, the lower bound, which was a, that is, say here, a, and b, say b is gonna be here. And we are going to calculate the integral of this function between two bounds a and b. Well, what does it mean? Well, it actually means to calculate the surface between the curve and the x-axis, okay, within this region a and b. So it's this surface. Well, to do that, numerically, you actually need to approximate. You need to approximate the surface below the curve. Well, how to do that? We use a method called Riemann Sums. Okay, Riemann Sums are based on splitting this region into smaller regions, and then we calculate rectangles. Okay, let me draw a simple picture. Assume that A is my starting point, and I also call it x0. Okay, and then I choose another point such as this, and I call it x1, and likewise x2, no, I didn't want to do that. x3, x4. I don't know why this is so crazy. Okay, x4, and the last one, the b bound, is equal to x5. Okay, so how do I compute the surface? Well, I have these subregions, these small almost rectangles, and what I do is that I take this point and evaluate the rectangle over here. Okay, this is a junk for me. So I take this point, the beginning point, like this, and I calculate the surface in here. Okay, I had better choose larger one. And for the second part, I take again the beginning point, so I take this thing and I calculate the surface here. Okay, in the third part, I again start with the starting point of the interval, make a rectangle like this, and calculate the surface. Okay. Fourth region is like this, and the last one just like this. So I hope you understand the basic principle. Well, if the regions are equally spaced, that means that the difference between x0 and x1 is the same as between x1 and x2. We call it, that would be the best case for us, and that would simplify our computations, and we call it the difference between those 2 points, between a and x1, x1 and x2, x2 and x3. We call it dx, like differential of x. Okay. Okay. So, well, assume that you do not have only, say, 1, 2, 3, 4, 5 regions, but you have a million regions. Then there is kind of a very small error, and you get almost perfect approximation of the region below the curve. Okay, and that is what we are actually then going to do numerically. Okay, so if we have this, we are sure that we are going to sum some rectangles, okay, where the base is dx and the height is the value of the function at the beginning point. Okay, so the area of the first rectangle would be a, the value of the function at a times dx. The area of the second rectangle would be the value of the function at x1 times dx, and we sum those all together, and we get the approximation of the function. Let me illustrate a simple example, but we are going to implement it in C++. Okay, so we start a new project. Oh, basically I have got it already here, so I just add the C++ file. I call it main. It's really not that important how you call it, and as usual, void main brackets, angle brackets. Okay, and then I define function that will return double, and it will stand for this function actually. Okay, so double function, it's a function of one variable of x, and say it will just return x. So what does it mean? That means fx equals x. Okay, now we are going to somehow implement the mechanism of the Riemann sums. Okay, so we definitely have some parameter. The parameter, it's up to our choice. We have to choose the number of the intervals. Okay, here we have 5 intervals, but if we want to reach a high precision, we can choose whatever number we want. Okay, so let's say I'll just do simple calculation. I'll start with n equals integer n equals say 5, such as in here. Okay, so then I'm going to integrate between the bounds a and b. So bound or low bound, that is a, according to this notation. Okay, it's the lower bound. Here is a low bound equals, say, 4, and the upper bound will be, I don't know, 7. So we are going to calculate the integral of the function between 4 and 0. Okay, and the function is just simply x. Okay, so the next thing we need to know is the dx, the differential, the base of the rectangle. Okay, so dx, it's obvious that it's the length of this interval divided by number of n. Okay, I'll just put here double, and dx definitely will be double. I just cast because we're going to divide by integer, and it will be upper bound minus lower bound. Okay, so this number minus this divided by the number of the intervals divided by n, and yeah, that's basically it. Now we are going to sum the stuff in here. Okay, but for that we create a function. It will be called sum integral, double sum integral. Okay, and we will be passing arguments low bound, double low bound, n, and dx. Okay, so like I said, we are going to sum the rectangles. Okay, so if it is sum, we are going to work with loop. So for integer I starting at 0, okay, because the first point is x0 actually, I is less than the number of intervals is n. Okay, but it's gonna be like this because n is not included in here, because the last one we sum starts by x4. Okay, so this is the last rectangle. There is no more rectangle over here, so 5 is omitted in our case. I++. Okay, and well, now we need to set up the number xi actually, the xi, double xi equals to low bound plus I times dx. Okay, so this will give us in every loop the number x0, x1, x2, and so on. Okay, And the last thing that remains to be done is to evaluate the function. Okay, so we call this function, evaluate it at xi, that will give us this point, and we multiply the height by the length of the interval, which is dx. Okay, so double function value equals value of the function in xi, so it's our function fun xi, and double the area of the rectangle is thus function value times dx. Okay, the height times the base. Okay, and notice that we are summing the rectangles, so we need some cumulative sum, say cum sum double, and it's initiated as 0 because at the beginning you have no sum and you are adding this calculated value. So cum sum plus equal to rectangle area. Okay, and we're gonna return okay. So that should be it. And let's try to compute something. So let's call the function here. Let's call double result equals sum integral low bound n dx. I'll try to compile this. I'm sure that there will be an errors because it's always like that. Yeah. Undeclared identifier. It's function value, and it's not some sum but sum. Okay, one more try. Okay, so fine. Okay, what's the dx? Yeah, looks reasonable. And how about this one? So again, as I said, we start by 4. We evaluate the function at 4. If we know that the function is actually the xi, so then we calculate the rectangle area. So we multiply it by dx and return the cum sum. So finally we get 15.6. Okay, so this is just a rough estimation because the precision is very low because of the small number of intervals. But if we are able to implement the code with 5 intervals, so we just increase the number here and we have some better estimation. So let's say we divide the interval to 1000 points. Now we get something more reasonable. So let me just put it into Wolfram Mathematica, and we type. Okay, so we start by 4 and by 7. and the function was x, and we are summing by dx, and if we want to numerically 16.5, and our result nearly the same. Okay, so this really seems to work. If we try to use it for some more complicated function, say x squared divided by 2 plus 3x minus x 1 divided by x, something like this, it should also work. (95.40). Okay, let's put it into Wolfram Mathematica. So instead of this, we just type x squared divided by 2 plus 3x minus 1 divided by x. I probably have written some error. I don't know where. That's definitely some kind of stupid thing I have written here. Let me try it once again. So it's 4, 7. Copy this. I know what went wrong. Okay, so let me define the function f of x equals x squared for sure plus 3 times x minus 1 divided by x. Yeah, that should be fine, and here we're just going to integrate the function f of x. Yeah, here we go. So 95.44, what was the result here? 95.40. So it's basically very close. It's just because of insufficiency of interval. So if we increase it to 100, yeah, we are almost there. Okay, so that was a simple integral. However, there are much more sophisticated ways how to approximate the value of integral. This is kind of slow, you know, but it works. Well, our task is not to describe how to implement numerical integration of simple integral, but double integral. So in principle it is the same, but it's kind of more deep in the code. Okay, so what's the difference? Well, we have the same beginning. We are integrating something, but then we have one more integral inside, and the upper bound is dependent on the value of y, okay, which is given by the outer integral. So this might look kind of demanding, but it's not that bad. Okay, well, what does it mean is that we will be actually having two loops. Okay, one loop within the other loop, and the upper bound will be changing dynamically, okay, based on the value of this. Okay, so let me implement the code. So I'll just copy this, and there will be some double integral. Okay, and also notice that in this example I have this bound given. Okay, the second bound is given, so I have to extend the code. So low bound 1, upper bound 1. This actually refers to these two bounds, these outer bounds 3 and 5. 3 and 5. Let's keep it simple now. And double low bound 2 equals 1. Okay. The upper bound we left here unspecified because this is given. This is somehow given by the value of y, which is uncertain for us now. Okay. So how to tackle this problem? Well, we have this this function here, and we are going to change it so that it fits to our problem. Okay, so it's basically iterating within the integral. Okay, so it's some kind of quadratic loop, which is kind of slow, but it works. Okay, so we start as before. We have some cumulative sum. Okay, we have some cumulative sum. Let's call it big sum, because there will be another sum in the inner integral. Okay, and we definitely want to keep this because we will be determining the value of determining the value of this. But notice that this is called dy, so let's call it dy. It's not that important. And this is gonna be a bound 1 and low bound 1. Okay, so now we are looking firstly at the outer integral. So we set up firstly yi. Okay, so instead of this we have y. And we are not going to evaluate the function, but instead of that we have to evaluate the integral. Okay, so let me think. We take this one, and this one will actually determine the upper bound. So ey in each loop will stand here. So we will be summing from 1 to yi. Okay, so we determine the value. No, not now, sorry, I'm kind of confused because this is really demanding on thinking. We have this one, and this will give us actually the upper bound of the inner integral. Okay, that we know for sure. Then we need to know what's the differential of the integral. Okay, we need to determine this. We know the differential in the in the outer integral, but we don't know the differential in the inner integral. Okay, so let's type double dx, and we know that the upper bound is actually this, and the lower bound is given by definition. Okay, we just need to pass some more parameters. So low bound 1, low bound 2, and let's see if it suffices or we need to pass some more parameters. Okay, so dx will be given as yi minus low bound 2 divided by n, and cast it as a double. Okay, so dx will be changing because yi will also be changing, moving up. So we have the differential for the inner integral, and then we need to, then using this differential we just calculate the value of the inner integral. Okay, so this is where the second loop comes into play. So we say for j equals 0, or j is less than n, then do j++. Okay, and what we are going to do, like before, we are going to calculate the value, but firstly we need to calculate xi. Double xi is equal to low bound plus dx times j. Okay, so we are moving from the low bound, and it's low bound 2 for the inner integral, so we are moving from the lower bound here to the iterated y. Okay, and yeah, here we compute the value of the function, and like before, we need to calculate the rectangle area. So we just take this. The rectangle area is, yeah, that should be fine. That's perfectly okay. Okay, so this is the rectangle area of the inner integral, and we introduce some variable, say double small sum instantiated at 0 in every loop, and this will collect the numbers of the rectangle area weighted by dx. Small sum plus equal to rectangle area. Okay, let's clean this up. And finally, if we have the value of this thing, we now have the value of this thing by the end of this loop, and the value is stored in this variable small sum. Okay, so we take the stored value and we multiply it by dy. So double second rectangle area is equal to small sum times dy. Okay, so this is what we are doing here. We have this value calculated and we multiply it by dy, and we collect in the cubic sum those values. Cubic sum is equal to plus equal to this value. Okay, and we are going to return cubic sum, and this should give us the correct number. I hope I haven't made any mistake. I just need to pass some more parameters here. Low bound 1, low bound 2, and dy. Yeah, that should be fine. And okay, so increase the number, say 200, and let's see what number it will return. So we are evaluating this strange function. So what we are doing now is that we have the numbers are fine, those are same as here. So for the outer integral it's 3 and 5, the bounds, and for the inner integral it's from 1 to y. Okay, so that's fine. And the function is not fx equals x, but it's fx equals x squared 1/2 x squared plus 3x minus 1 divided by x. So let's make it more precise. Okay, let's try it. And oh yeah, error as usual. J. Okay, some more. Okay, here it's low bound 1 because it refers to the outer integral. Does not take 4 arguments. Why? Because we have some double integral. Okay. So it starts calculating the outer integral. So it started by 3, calculates the dx, and now evaluates the inner integral between 1 and 3. Okay, you can see that the numbers here will go to 3. It's kind of slow, but you just have to trust me. And I'll skip to get in here. Return cubic sum. It returns 64 and something. Let's verify that. Okay. So what are the bounds? 3, 5, 1, y, fx, dx, dy. Yeah, that should be fine. 65.582. What was the number that we have obtained? Yeah, we're almost there. It's not perfect because you have some approximation error, but it's very close. Let's increase the number, but now it's gonna take a lot more time. Let's see how C++ is fast. Okay, 65.57. Almost there. Last try might be increase it to such number. It's gonna take much more time. Like I said, there are much more better methods how you can calculate double integral, but this is just the pure method given by the definition, okay? And it works even though it's slow if you want to reach some good precision. Hopefully it will end soon. Notice that the time for which it is running increases by square root as you increase the number of loops. Okay, so it doesn't take 5 times more from 10,000 to 50,000 because you have this inner loop that makes it more complicated. Go, 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 go. I hope YouTube is not going to impose some kind of time limit, because you know that some of my algorithms take some time. I hope it's still working. Let's pause it here. Ah, only 10,000 more. I think it pays off to wait. But you can see that if you increase this number rapidly, it takes a lot more time. Therefore, I'm also not suggesting this method to implement to some systems, but it's just for illustration how double integral works. Even one such as this. Okay, so it has disappeared. Why? But I hope you believe that that this number is even more precise than the one we had before. What was it? Sorry. This one only takes... Oh, I by mistake put here something like this. This should be much faster. You should hear my computer fan. It's kind of loud. So is it still working or not? Okay, once again. Yeah, should be completed within a second. I don't know why it crashes like this. Maybe because I need a breakpoint over here. Yeah. So 65.57. It's not that far from the exact number here. So that's basically all from me now, and just come to visit my channel again.